Rearranging rational equations. Many fields in math, science, and engineering have developed mathematical formulas to describe real-world relationships. A classic example is physics. Physics has lots of mathematical formulas that relate things like forces of gravity to the masses of objects, or the attraction that electrons and protons feel in an atom. And these formulas we need to be able to rearrange them in these subjects to isolate different variables. So you're going to see a few examples. To start with, we're going to start with an example of a rational formula that you've seen in math before, which is the slope formula. So the slope of a straight line m is equal to y2 minus y1 over x2 minus x1. And we are asked in this first example to rearrange / solve the slope formula for x1. So how do we do that? How do we rearrange an equation for x1? What that means, I'll talk about our end goal before we get to the process, is that we want to say x1 is equal to something. So right now x1 is down here in the denominator. That's a problem. We need to get it up into the numerator. So the first thing we're going to do to get it up into the numerator is get this denominator x2 minus x1 out of there. So we have to multiply each side by x2 minus x1, and that removes it from the denominator and puts it up into the numerator on the other side of the equation. But x1 is still not free. We can't just say x1 equals something, because now it's locked inside these brackets. So to get it out, multiply m into each term in that binomial. So I have m times x2 minus m times x1 is equal to y2 minus y1. Now we're doing a little bit better. Now we have x1, and it's on the left-hand side, and I can move away minus m times x2 from each side of the equation. So I'd have negative m x1 equals y2 minus y1 minus m x2. The last thing I need to do to finish rearranging this equation for x1 is to divide each side by negative m. And that would leave me with x1 is equal to y2 minus y1 minus m x2 divided by negative m. And so now I've finished my problem. I've rearranged this equation so that I have just x1 left all by itself. So the process for rearranging equations is going to depend a little bit depending on what the equation looks like. And the general idea, though, is to get rid of your fraction when you can. So that's what I did in green here. Got rid of my fraction as early as possible, and then isolated that x1 as much as I could. So I did that over here by removing that mx2 by subtracting it from each side, moved it over to the right-hand side of the equation, and then dividing by m. So it's like solving an equation, only instead of using numbers, you're using variables everywhere. But all the rules that we've learned are still the same. So in this next problem, we're going to try to rearrange this equation for c. So at the beginning, I have 1 over c plus 1 over m equals 1. And I need to rearrange for c equals. To start with, I could just try by subtracting 1 over m from each side, because it would get something away from the c. That should leave me with 1 over c is equal to, on the right-hand side, or sorry, on the left-hand side, those terms cancel. And on the right-hand side, I have 1 minus 1 over m. But the problem is c is now, it's in the denominator of the left-hand side. So this is not the same as saying c equals. So I have to get it out of the denominator in order to continue this problem. So to do that, I'm going to multiply each side by c. On the left-hand side, the c's cancel, leaving me with 1 equals 1 minus 1 over m times c. And from here, I could multiply c into the brackets, but I'm actually not going to do that because I'm really, really close to having c equals. I just have to isolate the c on the right-hand side. So instead of multiplying c in, I'm going to divide by 1 minus 1 over m. So if I divide each side by 1 minus 1 over m, that cancels it on the right-hand side, leaving me with just c on the right-hand side. And on the left-hand side, I have 1 over 1 minus 1 over m. And that is a perfectly valid equation for c. I have successfully rearranged this equation for c. There's other methods we could actually take to do this, but this is the method that just sort of, I saw at first, and I thought I could rearrange this successfully, so that's the method I took. But there are other methods that you could do that would also solve for c or rearrange for c successfully as well. So let's actually look at one of those other methods. So one way to look at this is it's like a rational equation that we looked at earlier, only with more variables. But we could go at it the same way, which is to multiply by that lowest common multiple that will cancel all the fractions. So if I multiply each side of the equation by c times m, that will get rid of the fractions on the left-hand side. So that would leave me with cm times 1 over c plus cm times 1 over m equals cm. On the left-hand side, c's cancel on that term, m's cancel on that term, leaving me with m plus c equals cm. So you can see that this method gets rid of all our fractions, leaving me with a nice expression that I can try to rearrange for c. Only the trouble now is my c's are separated on opposite sides of the equation. So I'm going to move the c on the left-hand side over to the right-hand side. So now I have cm minus c. And you think, well, we still have two c's, but I can actually factor those two c's from the right-hand side of the equation, which leaves me with m minus 1, c times m minus 1. And the reason I want to do that is I've taken my two c's, which are in separate terms on the right-hand side, and by factoring them off, I now have just a single c left on my right-hand side of the equation. And to finish isolating this, I can divide each side by m minus 1, leaving me with just c on the right-hand side and m over m minus 1 on the left. What's cool about this is that the equation for c actually looks a little bit different than our first solution for it. But they are actually equivalent. They are totally equivalent, and we could show that by rearranging the first equation, the first expression for c, by getting rid of that complex fraction. So I'll leave that as a problem for you to try to do. So I mentioned that in physics, it's a good example of a subject with a lot of rational functions in it. So one common example is the force of gravity. So the equation for the force of gravity depends on two objects with masses m1 and m2. An example would be you could have the Earth and the Sun, and we could calculate the force of gravity between them. The mass of the Earth would be m1, the mass of the Sun would be m2. And it depends on the distance between the two bodies, which is r, and this universal gravitational constant for g. At the end of the day, it doesn't really matter what any of these things mean, because if we're just asked to rearrange for m1, then we can go ahead and do that, regardless of the meaning of everything. That's one of the beauties of mathematics, is sometimes it doesn't even matter what you're working with, because as long as you're following the rules of math, you can still solve the problem. So we want to rearrange this equation for m1. So there's m1 in the equation. How do we get it all by itself? Well, when I look at this, to start with, I think I want to get rid of the denominator. I want to get rid of that r squared that's on the right-hand side with it. So to do that, I would just start by multiplying each side of the equation by r squared. Multiply the left-hand side by r squared and the right-hand side by r squared. That will eliminate it from the right-hand side, leaving me with fg, so that's f with a little g, that's one item, the force of gravity, times r squared, is equal to g m1 m2. Now to isolate the m1, all I have to do is divide by g and m2 on the left-hand side. That would eliminate the g and the m2 from the right-hand side, sorry. And on the left-hand side, I would be left with just fg times r squared over g m2. And all of that's equal to m1. So I've rearranged the equation for the force of gravity for mass 1.